wherever your data is coming from. And I have two missions. I need to do streaming analytics for my organization so that I know what's going on in real time. And I also need to do more complicated AI and reporting so I can predict what's going to happen in the future. How do you do this? Okay, let's get started. Step number one, not surprising, Spark. So Spark has pretty good streaming APIs, and so it's easy to connect to Kafka, do whatever processing you want, and create dashboards or real-time queries or whatever's going on. But that brings us to challenge number one. Kafka and streaming are great for answering real-time, what's happening at this moment in my business. They're not so good at answering longitudinal queries, what happened over the last 2 years. And so I've been reading a bunch of blog posts and talking to people about how you solve this problem. And I heard about this thing called the Lambda architecture, which, as far as I can tell, means you just implement everything twice. You have a streaming version, you have a batch version, and you run them side by side. And okay, so we can build that. It's actually pretty easy with Spark because we have unified APIs for streaming and batch. It's a little bit more to manage, but I can do it. So, okay, great. And now I can do queries off of my data lake, right? Everything's great. Finish my job. Okay, that brings us to challenge number two, messy data. As I mentioned before, the data coming in is garbage, so the data in my data lake is garbage. So I gotta fix that somehow. And so what I've seen people do is they build validation frameworks. In addition to their queries, they write a whole other system that runs other queries that check to make sure that the quality of the data is what they're expecting, and it throws alerts or emails you or does other things when something goes wrong. So again, I can build that. I have to run it in both places because I have this Lambda architecture thing going on. But again, it's not too much work. I can set it up, so I build my own validations. That brings us to challenge number three, mistakes and failures. So even though I have these validations, some data still snuck through before I put them in place. Now there's bad data in my data lake. How do I correct that? Well, so I've seen this pattern. You partition it by date or something. So you create a partitioning, you subdivide your data set into these partitions, date, hour, whatever makes sense for your organization. And then you build an engine that can recompute. So anytime I notice a mistake in one of my days, I just rerun that whole day. Now, as we just learned, good luck if you're on S3, because when you blow that directory away and recreate it, it'll flicker in and out of existence for a while, sometimes as many hours. But it's still possible. You just wait a long time and it'll work out. So I built this extra framework for reprocessing. Now I can handle mistakes and failures. And then, oh man, updates. GDPR happened. And now I have to go and remove everybody who's given a DSR against my organization. So I have to actually, allow people to be forgotten. I have to run this query. So, again, I can do that. I build some more Spark queries to do updates and deletes. I got to be really careful though, because if you modify your data lake while other people are reading it, they'll see inconsistent state and get the wrong answers. So I have to be very careful to schedule my GDPR jobs at one time and my reporting jobs at another time. But I guess I can do that. And so, okay, now we've built this whole architecture around the data lake. What's wrong with this? The problem is you're solving systems problems, not data problems. You're not focusing on what's actually bringing value to your business, to your organization. And really, I think of this as a bunch of data distractions. What's missing there? The problem is that when you just run Spark on top of these big cloud systems, you don't get atomicity. That means that when one of your jobs fails in the middle, it leaves out corrupted state, and then I have to manually worry about cleaning up. There's no quality enforcement. So bad data can just work its way through without any checks stopping it from happening. And there's no consistency or isolation. So this means that if you want to mix multiple jobs on the same table that are modifying it, your guess is as good as mine what's actually going to happen. If you want to do streaming and batch at the same time, good luck. So let's take a look instead with Delta Lake. So the idea of Delta Lake is we're going to take something that looks like this, and we're going to turn it to something like this. Now, before I go too far into this, I just want to clarify. I'm going to talk about this bronze, silver, gold category. A real Delta Lake looks something more like this. It's more complicated than there's just 3 tables. But I think it's really useful to think about these categories. And the way I think about them is these are reliability classes for data. And the power of Delta Lake is it gives you the tools that allow you to incrementally improve the quality of your data until it's ready to be consumed by your customers. And so what's so cool about this? Why should I even care about this? So first of all, Delta Lake brings full ACID transactions to Apache Spark. And that's even if you're running on an eventually consistent system like S3. So all those problems we just heard about, gone. It also gets rid of the listing problem too. In order to update a Delta table, it is at most 2 RPCs to S3, no matter how big the table is, which is pretty cool. It's fully open source, Apache license, no common clause nonsense. You can do whatever you want with it. It is powered completely by Apache Spark, and it integrates with all of the APIs. So streaming and batch, data frame reading and writing, all work out of the box. And I'll talk about that a little bit more in a little bit. So now let's actually kind of go through these patterns that I see evolve once you have a system that gives you these capabilities. So step number 1 is I see a lot of people create what they call bronze tables. The idea of a bronze table is it's just the raw data. I just read Kafka and I did minimal parsing and I dumped it directly into this bronze table. Now why did I do minimal parsing? Well, it turns out there are no bugs in a parser that you didn't write, which is great. So you just capture everything raw so you can come back and look at it later. And Delta supports storing massive amounts of data, so you can have very long retention, even years worth of data in your bronze data sets. Now, how do I move data between different tables in a Delta Lake? A pretty common pattern is using streaming. And I want to clarify a little bit here because there's a lot of misconceptions around streaming. A lot of people think that the only reason that you would do streaming is because you want low latency and you're willing to deal with the extra complexity in order to get that. And it is true, structured streaming with continuous mode can even do millisecond latency, but it can also do 1 minute latency, 1 hour latency, 1 day latency. There's this really cool mode where you can say trigger once. So a streaming job will start up, process anything that's new, and then shut down. You can turn the cluster off in between. So it's really not just about latency. To me, streaming is about running a query continuously that automatically updates the answers as new data arrives. And that's pretty much what you generally do with data. The cool thing about using streaming instead of batch is that streaming understands the concept of what's already been processed, what is new, how do you take that, process it, and commit it to downstream, maintaining exactly one semantics. It has checkpointing, it has failure recovery, and those are all things that you have to build yourself when you do batch jobs. And so I think streaming here can be used for low latency, but it can also just be used to ease the management of your pipelines. Now, of course, it's not all streaming. Batch jobs are very important as well, and Delta Lake fully supports those, including standard DML. So if you need to do retention, if you need to just dump a bunch of data into it, if you have GDPR, if you need to do upserts, we have full support for DML coming soon, in the next month. So standard insert, delete, update, and merge. We also support kind of standard high-level partition overwrites, including multiple partitions at the same time atomically. So now we've kind of cleaned our bronze data, we've got our stream that's pushing it down the quality pipeline, and it's moving on to silver. Now, silver is data that has been filtered, cleaned, augmented, joined with other interesting information, but it's maybe not yet ready for consumption. And so you might ask, why are you even creating a table out of it? And this is actually kind of an interesting thing that I've seen happen over and over again. One reason is maybe this intermediate data is useful to multiple people in your organization. So materializing it creates a point where everybody can share that data set without having to recompute it on their own. But a kind of more subtle benefit of doing this materialization is debugging. When there's a bug in my final table, if I can query the intermediate results, it's often easy to figure out where things went wrong. You can go back to the raw data, you can see the intermediate results, and you can finally see what came out. And that really changes the kind of data debugging story. And then finally, we end up with gold data. Gold data is clean, it's ready for consumption, it's high-level business aggregates that actually make sense to you and maybe even your CEO. You can read it with Spark, and today the Starburst guys announced that they're planning to build support into Presto for it as well. So this is kind of the next step. Now it's ready to do cool things with. One of the really cool patterns that I want to talk about, because of the patterns we talked about before, is recomputation. So when you change business logic, when there was a bug in your code and you want to recompute, that's actually really easy with Delta. And the reason is we've got all of the raw original data in bronze. And if I want to recompute downstream things, all I need to do is delete the table, delete the checkpoint, and restart the stream. The way streaming works is it guarantees that it will compute the same answer as a batch query run over the same data set. And the way Delta provides that guarantee is when a Delta streaming query starts, it takes a snapshot of the table at the moment that query starts. It breaks that snapshot into nice little incremental pieces, it processes them at one at a time, And then when it gets to the end of that snapshot, it starts tailing the transaction log, looking for new data, incrementally processing whatever arrives. So it both kind of does this nice backfill job, and if you're running in the cloud, you can spin up a giant 1,000-node cluster for that. And then when you get to the nice incremental part, you can scale that down. This is something I've seen a lot of people have a lot of success with. So who's using Delta Lake? Why should I care about this thing? So I should maybe give a little bit of history here. Delta Lake has been a product within Databricks for the last 2 years. It's used by many of our customers. It processed over an exabyte last month alone. And in the last month, starting at the Spark Summit last year, we announced that we're now open sourcing it, so it's available for everybody. But we use it kind of across the spectrum, including one really cool use case that inspired the creation of Delta, the incident detection and response team at Apple. And if you want to learn more about this, the whole keynote is available online. You should watch it. It's super interesting. But just for a quick summary, this guy, Dominique Brzezinski, runs detection and response. He has network sensors all over Apple's corporate network. It captures every TCP connection, every HTTP connection, every DHCP request that happens on any computer at Apple. So we're talking trillions of records per day, petabytes of data per week, and he ingests it all into one giant raw table, and then he has a whole bunch of streams from that pull out interesting events that, maybe an attacker, maybe some other interesting event. You can do correlations, you can figure out whose laptop had that DHCP address at that time, kind of interesting things like that. And then there's a team of 100 analysts around the world who are on call to respond to incidences, query this data to figure out the blast radius when something goes wrong. So, okay, how do you use Delta Lake if you want to? Let's take a look at that. So it's pretty simple. It's published on Spark packages. So all you need to do to add Delta to your existing Spark cluster is add a dependency to it. So if you're using a Spark shell, that's just one command line argument, -- packages. You can also add it to your Maven dependencies. And if you want to change your existing code to use Delta, that's even easier. All you need to do is change the format. So if you're using Parquet today, or JSON, or CSV, or whatever, all you need to do is change that to Delta. And everything should work the same as before, except now it's fully transactional. You get all the benefits I talked about before. One feature that I'm really excited about, this is something that we're actually working on this quarter that we're hoping to release later this year, really allows you to define more details about what data quality means to your organization. So data quality means a lot of things. It means the data should be discoverable, so you can say things like, it needs to be stored here, it needs to have exactly this schema, this table needs to be registered in the metastore, you can give human readable descriptions, and the idea of this is you can write this all down in code, and then Delta, when you go to deploy, will verify that all of this is true before your pipelines begin running. This allows you to version control the metadata about your data lake. There's one other feature that I'm particularly excited about called expectations. Transactions are great because they guarantee that everything that you said to happen is actually going to happen exactly once, atomically. It'll continue to happen, it'll be consistent and isolated and all that. But it doesn't protect you from bugs in your code. If your code has a mistake in it, the transactions will happily make sure that mistake is faithfully reproduced. And that's not great. So what expectations do is they allow you to also explain what quality means for your particular domain. So you can actually say things like, this is a timestamp. I know that my organization started in 2012. So if data ever arrives from before that, like say 1970, for example, I know something went wrong and I want to fail that record. So databases have had this concept for a while. They call it invariance. You can set an invariant on a table, and any transaction that violates that invariant will get aborted. We support that. That's kind of the fail mode. But what makes expectations powerful is they are designed for big data systems. If you fail any transaction that doesn't meet your expectations in big data, you probably won't get very much done. And so what expectations allow you to do is tune the severity. You can say, I just want to monitor what percentage of records are bad. Or I just want to abort if over a certain threshold of records are bad. Or my favorite feature is called data quarantine. The idea of a data quarantine is I can say records that are bad, don't stop the pipeline, just redirect those to another table so an engineer can come and look at them later and figure out how to remediate this problem. So this is, like I said, something that we're working on this quarter. We're hoping to release later this year. So now that I've given you the whole why Delta, who's using it, what would you want to do, I want to dive into some of the nitty-gritty details on how Delta actually works under the covers. So first of all, how does Delta work on disk? So as I said before, it looks pretty like a typical data lake. It's just a directory on the file system of your choice, S3, Azure Data Lake, HDFS, whatever. And we have a transaction log. this is kind of the key difference, is the transaction log is stored alongside the data. Inside of the transaction log, you have different versions of the table. And then we have optional partition directories. I say optional because there's actually a mode where you can turn those off and randomize the prefixes to be more efficient on S3. It's kind of a random detail, but and then also actual Parquet data files. So when you make a transaction against Delta, you start by writing out these Parquet files, but they're not actually part of the table until you make a transaction to add them. And that's how we get all of these nice atomicity and other properties. So what's actually in each one of these entries of the transaction log? So you can think of the state of a table as the result of applying a set of actions. So I'm going to walk through what those actions are. So the first one is change the metadata of the table. So you can say the schema of the table is now this, here's the name, here's the partitioning. You can add a file to the table. So you can say, I want this file to be there, and you can also support keeping optional statistics about the data in that file. You can remove a file from the table. We have this mechanism called set transaction. I won't go into too much detail here, but the idea is this allows you to atomically commit a little bit of metadata about what this operation was with respect to some kind of pipeline that is running. We use this in structured streaming to make sure that table streams commit to a table exactly once. Basically, they say this is batch 1 of stream X, and then when they the stream fails, you can go ahead and ask, did batch 1 commit or not? And if not, it can reprocess it. And then finally, we have this notion of protocol. This allows us to evolve the protocol over time, blocking older clients from reading the table if we make breaking changes. So the result is, you can now think of a table, once you walk through this whole set of actions, as its current metadata, a list of files, a list of transactions that have committed, and the current protocol version for it. So now there's a couple of tricks. Now that we've got the basic protocol, we've got the basic layout, how do we actually make that massive? How do you get the full transactionality? So step number 1 is this trick called log structured storage. So kind of like I mentioned before, changes in the table are stored in a log. And the important aspects of this log are it needs to be ordered. So we agree on a serial ordering for changes to the table. And also they need to be atomic. So when I add a file to the transaction log, that file must become completely visible all at once. And it turns out on the various file systems this is actually possible. S3 provides that out of the box when you create a new key. And Azure and HDFS, you can get this by creating a temporary file and renaming. So the idea here is we create file version 0, and it adds 2 files to the table. We create file version 1, and it removes those 2 files and adds them. But now these operations are guaranteed to happen atomically. They either happen completely or not at all. The next trick is mutual exclusion. How do we agree on that ordering of changes? And so the guarantee that we're going to need from our underlying system is if 2 people try to create the same version of the table, one of them needs to fail. You cannot allow 2 people to think that they have successfully created the same version of the table. So just to make this clear, user 1 can create version 0, user 2 can create version 1, and then if 2 people try to create version 2, one of them must get an error. And so on systems like Azure and HDFS, the file systems provide this. They're actually transactional. Rename will fail if the destination already exists. On S3, because it's eventually consistent, it specifically is not a lock service, you need an external thing like Dynamo or MySQL that can do this mediation and guarantee that only one person completes. Now, you're saying, wait a second, if every time somebody else modifies the table I fail, isn't that wasting a lot of work? Fortunately, we have a trick called optimistic concurrency that allows us to allow many transactions to occur at the same time if they don't overlap with each other. So I'm going to walk through the algorithm for that. So you start, when 2 people want to do an operation on the table, you start by recording the start version that you read that table at. So user 1 and user 2 read version 0 of the table. You record while the transaction is running, while their Spark job is occurring, both what they read from the table and what they write to the table. So in this case, I'm modeling 2 different streams appending to the table. So all they need to read is the schema, and all they need to do is add new data into the table. So then we go to commit. User 1 wins, user 2 loses. So what user 2 can do is they can check and say, has anything changed that I read since version 0? And the answer is no. The schema is still the same, so it's safe to continue and commit again. The system will automatically retry. You don't even know that this commit happened. The final trick I want to talk about is massive metadata. We were talking a bunch about millions of files, can take hours to list. I think that's a huge problem. And how does Delta solve that problem? Well, the trick is, I like to think about big metadata as big data, and fortunately we've got a big data system. You could just use Spark. So we take all of those actions, these add files and remove files, we turn them into a Spark data frame. We use Spark to process them, and we write them out as a checkpoint in a nice efficient format like Parquet. And now, when you want to query a Spark table, rather than go and list all of the files in the directory, you can just go to the most recent checkpoint. And you can say something like, I want all of the files that are in partitions that match this predicate. That runs as a distributed Spark job, returns the answer very quickly, and then you only go and query the files that it returned. This is like the fastest way to get that file list into the Spark execution engine that I think exists. So that's how Delta works. Now I want to talk a little bit about the roadmap and where we're going with the project. So, we just released this thing in open source. We're on version 0.10 last month, but we are rapidly pushing out a bunch of cool new things. So in version 0.20, which should be coming out in the next week or two, we're adding support for S3 and support for Azure Blob Storage and ADLS. In version 0.3.0, which we're hoping to do sometime in July, we'll be adding those DML commands, update, delete, and merge, Scala APIs for them first. Also this command called vacuum, which allows you to remove stale snapshots, so you do not have to spend infinite money on storage. And then the rest of Q3, basically our plan is to take a lot of the cool things that we built inside of Databricks and open source them. So we want to put full DDL support, create table, alter table, support for storing your tables in the Hive Metastore. And we also want to add SQL support for running standard SQL, update, delete, and merge, in addition to those Scala APIs that we're doing a little bit sooner. So if you want to learn more, I encourage you to go to our website. It's delta.io. You can check out the source code. There's also links to our mailing list and our Slack channels. My whole team is in there every day, so if you have questions, if you want to learn more, if there's features that you think are missing, let us know. We're super interested. Then I think I'll take some questions.
Thank you, Michael.
We had one right there.
All right, who's the first one?
There you go.
It was super interesting. It was super interesting. The main things that I wanted was, one was the bronze stage, where you actually store raw events. Can you query it by type, in the sense that give me exactly between this period and it should exactly?
Yeah, that's a great question. So, so first of all, bronze is just a concept. It's just data that is still dirty that you don't trust it yet. It's not ready for consumption. It's definitely not ready for consumption. Now, there's a bunch of tricks you can play. So a standard trick that I see, especially for bronze tables, is you partition it by date. So now it's very quick to look up a date. And then we also have kind of statistics-based skipping tricks that we're planning to open source that allow you to do slightly better. We record the min and max values for any given column for each file. And so we can say, if you're looking for this time, and this file only has these times, skip that file, don't look at it. So both of those can allow you to be pretty quick at finding the files that are relevant.
This is one thing you touched on as an exception, like reprocessing. But for us, reprocessing is pretty standard. Like you have data and you have rules. And people want to see how it will look like and the rules apply. So is it something standard that we do, or how will that look like?
So my point about reprocessing was it's kind of fundamentally supported by retention and streaming. So all you need to do, normally you have to kind of build this separate framework and think about it. You have to think about backfills, and you have to think about once the backfill is complete, then you want to switch to incremental processing. The idea here is with Delta, you just don't have to think about those concepts. But I think it's pretty easy. I think it's supported out of the box, is the way I would describe it. And it doesn't necessarily have to be the method that I said, right? If you want to, let's say you have a pipeline that's running. You've read from a Delta table, you have a stream that's written to another Delta table, and you've decided, I want to see what this would look like. You can just make a new table with a new checkpoint. Basically, anytime you create a new checkpoint, it will start that query over from scratch and reprocess from the beginning of time. Anytime you use the checkpoint, it will incrementally process only what is new since that query last ran. And by kind of either using the same checkpoint and creating a new one, you can decide what semantics you want.